Okay, so the continuation of what we're looking at here, and actually this is the last part of this unit, is something called percentage yield, or it's also referred to as percent yield. So this is where we're going to start talking about how much product is made, but we're going to compare it to how much product actually should be made. Okay, so very rarely do you have what happens in real life matching your prediction. So for example, let's say we had a reaction and we did our stoichiometry, right? So we did our regular stoichiometry and we found, okay, we're supposed to get 5 grams of C, right? According to my calculations. When you go to actually do the reaction in real life, maybe you only got 4.8 grams instead of 5. So first of all, the term yield is always in reference to a product. So sometimes you can say a product is a yield of the reaction. So it's like a result. So percentage yield or percent yield is basically comparing what did we actually get in real life when we did the experiment and compare it to what we should have got according to our calculations. Okay, so anything you determine from calculations is known as what is called theoretical yield. So in theory, we should have gotten 5 grams, but in real life, we got 4.8 grams. Right? And that can happen for various reasons. But percent yield is basically doing a comparison ratio between the two things. Okay, so some terminologies, I've mentioned already a few of this. So theoretical yield is the amount of product that is done through stoichiometry. Okay, so in other words, this is what we are going to calculate from our calculator. How much should we have gotten? So how much product should be made? Actual yield is essentially the experimental yield, or the amount that is really obtained from an experiment. So the actual yield is essentially the real life product amount. Okay, and essentially percent yield is a ratio comparing those two things. So it compares the mass that we get from an experiment and we compare it to the amount we were supposed to get from stoichiometry. Okay, so what are some reasons why we get less than what we're supposed to? So low yield means lower than 100%. So this is the example I started off with. We really got 4.8 grams, but we were supposed to get 5 grams, right? So we have a lower amount of yield than what we should have gotten. Okay, so there's a couple of reasons. The first one is within your control. So this is a source of error that is done through experiment. So maybe there was just an error that was made. So this could be a human error or whatnot. But an error was made while conducting the lab. Okay, so the first one is something that is within a person's control. Okay, the next ones I'm going to discuss are things that can happen even if you are very careful and following the experiment to the best of your ability. Okay, so the second point here is impurity in the reagent used. Okay, so different chemicals have different purity levels. Okay, so they call them grades. I'm going to give you an example. So let's talk about salt for a second, right? So sodium chloride is essentially table salt. So the salt that we would use in a lab is not the same salt that you would put on your food, okay? Because it's a different purity level. So some grade levels that can include our food grade levels. So meaning it's pure enough to consume, but it's not 100% pure. We can have what's called essentially crude level, or this can be like an environmental grade level. So this could be like the salt that's on the road, like road salt, right? So the salt we put on the road, the salt you put on your food, and the salt that we use in a lab, so we call that lab grade, or sometimes it's also referred to as analytical grade. these are all made up of the same substance, but they're different purities. I don't know if you'd want to take road salt and put that on your food because it's a much lower purity. Now, lab grade you could put on your food, but lab grade and an analytical grade becomes very expensive. Now, the difference in the purity between these three things, just for this example here, is actually probably not so much. So let's do, I'm just going to look, for example, I'm going to look this value up. Salt purity in road salt. Okay, so it's not great. You're looking at about a 60% purity level. Okay, just to compare. So that means 40% is other things. So it could be sand, it could be other types of salts, etc. Okay, so now let's check out food grade. Food grade in Canada, it's also important to keep in mind that food grade in Canada is different from food grade elsewhere. So food grade can be anywhere between 99.7 to 99.9% pure. Now that's pretty good. I'm gonna chalk that up to being in Canada, okay? Because that amount of purity is not everywhere. So now let's look at salt purity in lab grade. So lab grade salt, we are looking at 99.9%. Okay, so you can have less than that in your food, but it's pretty darn close actually for this particular example. Now, other compounds, you can have lab grade being 98%. Obviously, we don't eat every single chemical. That just so happens to be for this example. But essentially, the more pure a substance is, the more expensive it becomes because they have to essentially purify it, or they have to separate it from other things. Now, even if you have the highest grade possible, there is nothing that can guarantee 100% purity. And the reason why is just simply even in manufacturing. So if there's a manufacturing process, as long as if there's like a speck of dust that gets into the container, they cannot claim 100%. So you'll never see a 100% pure substance, even at the analytical grade. And that's simply because they cannot guarantee that product. Okay, so no matter what, there's going to be some amount of impurities. We're kind of getting away from what we're trying to talk about here. Okay, this one you may or may not have occur. Sometimes there could be a side reaction happening, and other products are being formed that are not known to us right now. So maybe the reason why we only got 4.8 grams is because some of our reactants created a different type of product that we're not accounting for. So some of that matter has been removed in another reaction. And lastly, some reactions, again, this doesn't apply, these last two don't really apply to every situation, but some reactions are also reversible. So meaning maybe some of the product that we did make became reactant again. Okay, so this last point about reversible reactions is not really the focus for us here. We're not going to go into why that can happen. But if you decide to take grade 12 chemistry, we actually spend a whole unit talking about it. This last bullet point here, this last number 4, is actually a huge concept that we spend 2 chapters worth of time discussing. So it's very difficult for me to do that in a 2-minute section here. But anyways, so just know that that can be a factor that can affect the reason why we don't have as much product as we should. Now, sometimes when you're doing a lab, you may get more than 100%. So let's say we were supposed to get 5 grams, but we did the experiment and we got 5.08 grams. It's like, well, what happened there? So really, in theory, the only time you should get a yield of more than 100% is only through error. Okay, so there's nothing natural that would cause this to be more. It's just simply part of the experimental process, that either something wasn't removed, like for example, maybe you had to dry out some water and there's some water left behind, but regardless, there is something there that is impacting the mass. So here is our calculation for percent yield. So actually, just like when we looked at limiting reagents, the steps of stoichiometry are exactly the same. The only difference is percent yield can be added on at the very end to try and determine essentially how close the calculations are to what was obtained in real life. So the calculation is actually very simple. Your top number, the numerator, is your actual yield, or the yield that came from a real experiment. The number that's in the denominator is your theoretical yield, which is basically your calculated value from stoichiometry. Okay, times 100. So just like with everything else, right, we have to do some examples. I'm going to do 2 with you. This first one is kind of a little warm up to get you going, and then I'll do one that's more realistic, and then I'll have you try one out as well. So in a particular experiment, 10 grams of sugar should be produced. Sometimes you got to interpret the language here, but only 0.664 grams is produced. What is the percent yield? So percent yield is always the actual yield over the theoretical times 100. So the actual yield that we got from the experiment was 0.664 grams, and we should have produced 10 grams times 100. So we're going to express this as a percentage. 0.664 divided by 10 times 100. So here we get a value of 6.64%. So that's a very low percent yield, right? So that means, so it's nowhere close to 100%. So it's a low percent. So remember that percent has nothing to do with significant digits. I would recommend to keep the digits there instead of rounding this to 7%, but you're not going to have marks deducted here for the yield number. Okay, so let's look at, so that was very quick, just to kind of get you used to the idea of this calculation. So let's look at one that involves a chemical reaction. So aluminum reacts with oxygen to form aluminum oxide. If 635 grams of aluminum oxide is obtained from reacting 1,150 grams of aluminum, what is the percentage yield? Okay, so we have the amount of reactant, and they're telling us how much was actually made. So this 635 grams is basically our experimental or our actual yield. We have to first calculate how much should we have gotten by doing stoichiometry, and then we can do our percent yield at the very end. Okay, so we're going to follow our regular stoichiometry rules right now so we can calculate our theoretical yield. So the first thing we do, we're going to do our balanced reaction. So we have aluminum plus oxygen making aluminum oxide. And then we need to balance this here. Okay, so we have the mass of aluminum itself, and we want to know the mass of aluminum oxide. Okay, so the biggest mistake I see here is students forget that they have to do stoichiometry because they say, oh, but they gave us the mass right now. This is the mass from the experiment. We want to know how much should we have gotten. Right? We're not able to do that until we calculate it out through stoichiometry. So this is not a limiting yield problem. This is not a limiting reactant problem, because remember, we were given only one mass. So this is kind of nice. It's like a regular stoichiometry problem. So this next thing we're going to do is we're going to find the moles of aluminum by doing mass over the molar mass. Molar mass is just 1 aluminum. Okay, so we'll continue this in the next part.